Welcome to This Explainer. If you've ever spent any time in a chemistry lab, you probably know thin-layer chromatography, or TLC, as that incredibly common, seemingly simple technique used to separate components in a mixture. But today, we're going to look way beyond the surface. We are diving into the deceptively complex, microscopic chaos happening at the molecular level.
Today, we're mapping out this journey step by step. We'll hit the basics of TLC, the three-phase system, the equilibration problem, why spots elongate, the speed of migration, and finally, maximizing separation efficiency. Let's get right into it.
Section 1. The basics of TLC, more than just a spreading dot.
When you look at the physical steps, it really seems like a piece of cake, right? You just dab a small sample near the bottom of a silica-coated plate, pop it into a chamber, and let capillary action draw the liquid solvent right up. Maybe you spray a reagent on it from a rubber pump atomizer, stick it in a cabinet with a video camera to grab the image, and then integrate the chromatogram. Macroscopically, it's literally just a handful of physical steps.
But here's the million-dollar question for today. Why is this supposedly simple technique actually way more complex under the hood than a highly automated setup like high-performance liquid chromatography, or HPLC? What makes this little glass plate so incredibly chaotic on a molecular level?
Section 2. The three-phase system, a fragile balance.
This is where the plot thickens. In TLC, we aren't just dealing with a liquid washing over a solid. It's a highly dynamic three-phase system. You've got the stationary phase on the plate, the mobile phase creeping up, and this is the kicker, the vapor phase filling the chamber. Inasmuch as this vapor phase is in constant equilibrium with both the mobile and the stationary phases, it creates an environmental balancing act that you just don't see in the pressurized closed tubes of HPLC.
Now, just like in HPLC, the actual migration is a rapid-fire sequence of adsorptions to the solid surface and desorptions back into the liquid. It's a chaotic dance. But in TLC, this dance is governed by three specific, highly complex phenomena that are entirely unique to this open, three-phase setup.
Section 3. The equilibration problem, a rush start.
Okay, phenomenon number 1. Before your compounds even budge, the stationary phase on the plate, is only partially equilibrated with the liquid phase. Think about a column system for a second. You can just pump solvent through until everything is perfectly stable before you ever inject a sample. But in TLC, that solvent front is aggressively pushing into dry, unequilibrated territory. So right out of the gate, your molecules are dumped into an inherently unstable, shifting environment.
Section 4. Why do spots elongate? The molecular traffic jam.
Which brings us to the second phenomenon. Have you ever noticed how nice, tight, circular dots often smear out into these long ovals? Well, that happens because the adsorption capacity of the surface actually drops significantly when parts of the adsorption sites are occupied. It's exactly like a crowded parking lot. The leading edge of your sample grabs the best, most available spots on the silica. With those sites taken, the capacity diminishes, and the molecules trailing behind are forced to physically spread out further up the plate just to find a parking spot. And boom, you've got an elongated spot.
This spot elongation points to a massive pitfall in planar chromatography. Because of this molecular fight for parking spaces, the retardation factor, or RF value, of a compound in its pure state is going to differ completely from the RF of that exact same compound when it's present in a mixture. In a mixture, it's constantly competing with other substances for those limited sites, which completely changes how far it travels.
Because this competition is so fierce, our source text drops a crucial piece of advice. Knowledge of the allotropic properties of each solvent is incredibly useful. Allotropic property is really just a fancy way of saying the solvent's eluting power. If you're trying to pull apart a complex mixture where molecules are battling for surface area, picking a solvent with the exact right competitive strength is literally your only shot at getting a clean, readable separation. Section 5. The speed of migration, a slowing front.
All right, phenomenon number 3. This is where a little bit of math steps in. The speed of migration of the solvent front is absolutely not constant. Unlike a mechanical HPLC pump that shoves liquid through at a totally steady rate, the TLC solvent front moves via capillary action. And because of that, it's a complex function that continually, unavoidably, slows down as it gets higher up the plate. In fact, this migration velocity is perfectly described by a quadratic function. X squared equals k times t. Here, x is the distance of the migration front, T is time, and K is a constant that depends heavily on the size of the stationary phase particles. Since distance is squared relative to time, the further the solvent travels, the more drastically it slows down.
Because of this built-in deceleration, the resolution between two spots on your plate depends enormously on their RF values. According to the data, resolution actually hits its maximum for an RF value of about 0.3. If the RF is too high, the spots have traveled too far with that slowing solvent and they start to diffuse. If it's too low, they just haven't separated enough yet. So, 0.3, that is your mathematical sweet spot for clarity.
Section 6. Maximizing separation efficiency. The final challenge.
So when we piece together all this microscopic chaos, the partial equilibration at the start, the spot elongation from molecular traffic jams, and that constantly slowing solvent front, what does it mean for the technique's overall efficiency? Well, in summary, it means the efficiency, or N, of a TLC plate is highly variable. It changes constantly depending on how far the spot travels, the specific mixture of components, and that shifting vapor phase equilibrium.
Let's put TLC head-to-head with HPLC to really hammer this home. Yes, both techniques share a minimum theoretical plate height, meaning they both have a baseline capability for separation. But here is the critical difference. TLC leaves you without a major control lever. In HPLC, you can easily turn a dial and vary the flow rate of the mobile phase to increase separation efficiency. In TLC, you absolutely cannot. Your flow rate is entirely at the mercy of capillary action and particle size. You are completely locked in.
Which leaves us with a final, provocative thought to take away from this explainer today. If you can't just twist a knob to control the flow rate and boost your efficiency, how will you master the elements? How will you perfectly balance that three-phase equilibrium, nail the exact allotropic power of your solvents, and target that 0.3 RF sweet spot to achieve the perfect separation? The microscopic chaos is definitely there, but with the right chemical knowledge, you have everything you need to conquer it. Thanks for hanging out with me, and keep exploring the incredible science hidden right there on the surface.